Let's imagine that we have a beam which is attached as follows. Whenever you're going to be facing a beam in this class, the beam is going to be your system, because the question would be most likely, what are the forces from the wall acting on the beam, or all the contact forces from the cable and from the wall acting on the beam. So let's do a free body diagram. Let's imagine that we're given the mass of the beam. The mass of the beam, or the mass of every system, will always be located at the center of mass. So we will always assume that our system is homogeneous. So for us, it would be in the middle of the beam. Let's imagine that we're given the length of the beam. What else? Obviously, if the system is the beam is going to be subjected by a force due to the cable, tension. If those two forces are the only force, obviously this beam cannot be at equilibrium, which is, again, our condition, static equilibrium. So there's going to be some forces coming from the wall. Every time you're going to see a beam that is attached to a wall, at this particular connection, which we call support, you will always need to assume two forces. One coming from the wall, which is what we used to call the normal force, N, perpendicular to the wall, and friction. Obviously, static equilibrium implies that we're dealing with static friction because the system is not moving. And now the tendency of that particular point is to obviously slide down. Therefore, static friction must be up. And we're going to call this Fs. Next semester, if you take C270, you will forget about Fs and N. You will use and learn a little bit more about supports and various types of support. And based on the type of support, you will either consider AX, AY, which will be replacing N and Fs. And then you will be adding a new type of piece, which is called coupled, for specific type of support. For us in this class, we will not consider couple, only two forces. One coming from the wall, normal force, and obviously a static friction that keeps that particular point from not sliding. Because we're always going to use that condition in this class that we never slip. In C271, you're going to study the slipping case. All right, so we have 1, 2, 3, 4 forces, but we are given the mass, therefore we are only facing 3 unknown: the tension, normal force, and the friction. Since the system is in static equilibrium, we know we can come up with 3 equations. That's it. Common pitfall of this situation is the system. The question will always ask you what are the external forces acting on the beam or the ladder or blah, blah, blah. Therefore, do not skip the first step of Newton's law, Newton's method, which is identify your system. Be very clear about which system you're identifying. A common mistake here is to consider beam and cable as one system. And so people start to consider forces here. If you consider the beam as your system, there's nothing to consider there. Okay? All right. We are going to need an angle. So if we consider this as alpha, we can express alpha easily by geometry, arctangent of G divided by L. All right, so let's apply Newton's law. Let's pick a coordinate system. I'm going to pick the usual, y and x, and I'm going to center it at this point, O, which is also the point about which I'm going to calculate the sum of all the torques. Let's write down Newton's first law in translational form. Back to chapter 5, which is again back to chapter 2. Let's review. Let's go fast on it. We're going to just pick up N, W is 0, Fs is 0, and negative T cosine alpha. The sum of those two is 0. In the y direction, Fs, negative W, plus T sine alpha. So far so good. Nice, easy, and nice review. Again, we're facing 3 unknown, Fs, N, and T. Therefore, we need one more equation. Let's calculate the sum of the torque. And let's pick O. The reason why I want to pick O again is technically I should have as many terms as I have forces. So I need to consider the torque due to Fs, the torque due to N, the torque due to W, and the torque due to T. And the sum of all those has to give me 0 vector. If I pick point O, then by property of the cross product, right away, 0, 0. That will make my life easier. The torque due to W is trivial enough. Well, I don't have to set up the matrix. I just need to take the component which is perpendicular to W, which is L over 2, and is going clockwise, therefore negative. I'm sorry, I should use mg everywhere to be consistent. And then the torque due to T, this one is a little bit trickier. Either you sit into D, that would be the whole length L, and you're going to take the component of T which is perpendicular to it, which is T sine alpha. Then you look at the direction. In this case, the direction is counterclockwise, therefore positive. Or set up the matrix as usual, just to be safe. The position vector is from O to B, therefore it's L, 0, 0. And the force T, we already did here. Minus T cosine alpha, T sine alpha, 0. The sum of those two is 0k. Therefore, what's left is L over 2 mg k plus LT sine alpha. K is equal to 0k. K shows up in every term. Therefore, we have now our third equation. One, two, three. The three unknowns are N, Fs, T. Boom, bada boom, easy. The rest is just math.